Okay, here are a couple more examples involving the method of substitution. So here I have an integral for x squared over x cubed plus 2 dx. I want to find the antiderivative. I'm going to try to use substitution. So first I need to regard this as a composition, have a composition here. One telltale sign here is that I have two parts. I have an x cubed plus 3 and I have an x squared, and if you look at this, the derivative of x cubed plus 2 is 3x squared, which is very close to x squared. It only differs by a factor of 3, just a constant. So I'm going to think of this as being the derivative of this, so that's going to make me think this should be u. Choose this to be my u. And in fact, here the composition, although it's not so apparent, can be seen better if you write x squared x cubed plus 2 to the minus 1 dx, right? That's the same thing because dividing by x cubed plus 2 is the same as raising x cubed plus 2 to the minus 1 power. And here you actually do see the choice of u. It's inside the parentheses, etc. Here it's a little bit less obvious, but the idea is that the derivative of x cubed is essentially the same as x squared, so you might try substitution. So I'm going to choose u equals x cubed plus 2 and see if it works. Might not work, who knows. I take du, the derivative of this is 3x squared plus 0 dx. And now I'm going to do my substitution, my change of variable from x to u. So I see that I got my x squared here, dx, and I have my x squared dx here. And they're so it's almost the same as du, except there's this 3 here. So what I do is I divide both sides by 3. I get 1/3 du is equal to x squared dx. And now there's a perfect match between the x squared dx and the x squared dx here. So for this numerator, I'm going to substitute in 1/3 du. That's going to replace this part here. And then the denominator, well, x cubed plus 2 was the same as u. So I'm going to substitute in the denominator, just substitute in the u. So altogether, what I have is this integral. And I can move the 1/3 outside the integral sign, just a constant. So now I'm left with integral du over u. Now, how do you do that? Well, that's actually a power function. We know how to do it, so we can use the power rule. We first have to make it apparent. What we're going to do is, just like we did over here, we can write 1 over u as u to the minus 1. So that's just algebra, right? So u can be brought to the numerator if we put a minus 1 power on it. Now we remember that the derivative, the antiderivative of u to the minus 1, it's not u to the 0. No, it's ln of u. Or if you like, the antiderivative of 1 over u is ln of u, I guess with the absolute value signs. So we have this 1/3 that comes from here, and then plus c. So that's almost it. We just have to back substitute x cubed plus 2. So we get 1/3 ln x cubed plus 2. And then we add our constant. So that's it. Okay, so let's see another example. The next example is a little bit more tricky, maybe. So here's one way to look at it. We got this complicated function. We look at the most complicated part. It's the ln of x. We want to make it less complicated by doing u substitution. So if we let this be the u, well, do we get the 1 over x somewhere? Well, yeah, the derivative of ln of x is 1 over x, and here it is. It's 1 over x. So it looks like it may work. So let's try u equals ln of x. In general, yeah, whatever is the most complicated thing, you want to break it up. In this case, the ln of x is the more complicated thing. So du, in this case, is going to be 1 over x, or x to the minus 1 dx. And so what I see is that 1 over x dx is right there. So I can write, instead of writing this green stuff, I can write du, right? Because 1 over x is the same as du. And then I substitute in for ln of x. ln of x is the same as u, so I can write du over u. And just as we saw before, the antiderivative of that is the natural log of u plus a constant. But then I have to back substitute ln of u, and u was ln of x. So in this case, it's ln of ln of x plus c. That's it.